Hello, this is Dr. Hanaa Assil, and this is Unit 4 of January 2021. This is in the Pearson Edexcel International A-Level, that is the A2 Chemistry Edexcel. So let's take a look at the questions and discuss the answers. So the first question says, which of these has the highest standard molar entropy at 298 K and 1 atmospheric pressure? Remember, which ones have higher standard molar entropy? You should remember that gases are more than liquids, more than solids, because as we go from solid to liquid to gas, it gets more random, so that is more entropy. So we're choosing a gas, not a solid or a liquid. Then between the gases, you should know that a more complex molecule would have higher entropy. More complex would mean that it has more electrons, or larger molecules, these would have higher entropy. So out of the choices that we have carbon dioxide would be the highest molar entropy among these choices. Okay, question 2 says the entropy change of the surroundings and the entropy change of the system for 4 different reactions are given. Which of these is thermodynamically feasible? First of all, how do we know if something is thermodynamically feasible? You should know that if it is an exothermic reaction, that means the delta H is negative. And if the delta S total is positive. So we want, if we're talking about delta H, we want it to be negative. If we're talking about delta S, which is what we're talking about here, then we want the delta S total to be positive. Now, what is delta S total? Delta S total is delta S of the system plus delta S of the surroundings. So which of these would have a delta S total that is positive? Well, that is P and Q. Which equation represents the standard enthalpy change of atomization of bromine? So let's remind ourselves first, what is standard enthalpy change of atomization? Standard enthalpy change of atomization is the enthalpy change that takes place when 1 mole of gaseous atoms is formed from its elements under standard conditions. So we're looking for something that gives 1 mole as a product. So that means B and D are wrong. I want to get 1 mole, and I want to start from the elements under standard conditions. Now, what is the standard condition of bromine? Is it a liquid or a gas? Remember, standard condition is the state at room temperature and pressure. You should know that bromine at room temperature and pressure is a liquid. So this would represent delta H for that reaction in A would be the delta H of atomization. This question is about 4 ionic compounds. Which of these would be expected to have the least exothermic lattice energy? Least exothermic means less delta H of lattice energy. Now, what is lattice energy? You should realize that lattice energy is the enthalpy change when 1 mole of an ionic compound is formed from its gaseous ions under standard conditions. So which of these would have the least exothermic? Well, to have the least exothermic, we're looking for a cation with bigger size, so a larger cation, and charge decreases. So I want one with lower charge. So I'm looking for the cation that is larger in size, lower in charge. So lower in charge means I want group 1, not group 2, so that it has only +1. Bigger cation would be the one down, so that would be potassium. So the cation is potassium, and the potassium bromide would have the least exothermic lattice energy among these choices. Which of these compounds would be expected to have the largest difference between the experimental value of lattice energy, which we usually get from the von Haber cycle, and the theoretical lattice energies? Well, the one that has the largest difference would be the one that has more covalent character. And that means more ion polarization. So the question is, which of these would be likely to have more ion polarization? Now, how do we get ion polarization? If the cation is small with bigger charge. So we're looking for a cation that is small, so above, not below, with a bigger charge. So that would be the magnesium chloride. So that would have the largest difference between experimental and theoretical lattice energies, because out of these choices, this is the one that would be more likely to have some covalent character. Question 5 says the standard enthalpy change of solution of potassium chloride is plus 17. The solubility is 359 grams per decimeter cubed. Which of these explains the solubility of potassium chloride? So why does potassium chloride dissolve a lot, or there is high solubility in water? Well, let's take a look at the choices. Well, the first one says hydration enthalpy of potassium ions and lattice energy are both exothermic. Well, we said the lattice energy is the enthalpy change when 1 mole of an ionic compound is formed from its gaseous ions under standard conditions, and you should know that lattice energy, when we're forming an ionic compound from its gaseous ions, it is always exothermic. So the fact that he's saying this explains why it is soluble, no. All ionic compounds would have a negative lattice energy. Also, enthalpy of hydration is the enthalpy change when 1 mole of gaseous ions dissolves in sufficient water to give infinity. Please know all of these definitions. You're required to know these definitions. And you should know that hydration enthalpies for any ionic compound are always exothermic, or they're always negative. So statement A is correct, but it doesn't explain, because this is correct for all ionic compounds. So why is it that potassium chloride is very soluble? This is not explained by A. B, of course, is wrong, because we said hydration enthalpy and lattice energy are always exo, not endo. Option C says the total entropy change when KCl dissolves is positive. Yes, if the delta S total is positive, then the reaction is feasible. So that allows the potassium chloride to dissolve. Of course, if the total entropy change when the KCl dissolves is negative, that's wrong. That would not make it soluble, actually. So my correct choice is C. Then question 6 says the total entropy change delta S total of a reaction at 298 K is minus 85 joule per degree Kelvin per mole. What is the value of the equilibrium constant for this reaction? Now, what is the relationship between delta S total and equilibrium constant? You should know that delta S total is R ln K. So I can rearrange that and try to get ln K. We put in the delta S total. R is 8.31. This gives me a value, and from that I can get that K is 3.61 times 10 to the minus 5. Propanone reacts with iodine in the presence of a catalyst of dilute hydrochloric acid. The reaction occurs in aqueous solution. The rate equation for this reaction is this. What is the possible mechanism? So you can see that the rate equation includes concentration of the propanone times concentration of H+. And that means I shouldn't have iodine in my slow step. So which mechanism do we choose? We choose a mechanism in which the slow step includes only the ones that are included in the rate equation, whether it is the first or the second. So if the slow step is the first, then that's it. That's what we include. If the slow step is the second, then we include the reactants in the first and second step. So where do we have a mechanism that includes 1 concentration to the power 1 of the propanone and concentration of H plus to the power 1? If you look at A, you can see that there is an intermediate that is formed in the first step and used up in the second step, so that's okay, they cancel. That's just an intermediate that is cancelled, and that means if we take the slow step, then the slow step includes the concentration of everything before it, so this would be the correct mechanism. The others are not correct. They will not include concentration of propanone and H plus. Remember, we're looking at the reactants, not the products. The rate equation for a reaction is this. So it is second order with respect to A and 0 order with respect to B. What is the value of the rate constant? Now, if we rearrange that equation, then that means the rate over concentration of A to the power 2. Of course, anything to the power 0 is 1. So there's no need to include it. So K is this value, which is the answer in C. This question is about weak acids. So we have pKa of ethanoic and pKa of chloroethanoic. Now the first question is, what is the pH of a 0.1 mole per decimeter cubed solution of chloroethanoic acid? How do we get the pH of a weak acid? Remember that for a weak acid, I can use this. Concentration of H plus is the square root of Ka times C. So we have the pKa, we can get the Ka. Remember that the Ka would be 10 to the minus pKa, so that's the value for Ka. I can put that in and get the concentration of H plus ions, so I have the value of Ka, and it already gives me the concentration is 0.1. So this is concentration of H plus ions. Now how do we get pH from that? pH is minus log the concentration, so the pH comes out to 1.95. Which is the acid conjugate base pair in the reaction between ethanoic and chloroethanoic? So we have ethanoic acid plus chloroethanoic. Which of these will act as an acid and the other will act as a base? Remember, we look at the pKa's of these two weak acids, and you should know that the one that has higher pKa is less acidic. So if I want to start with acid and end up with its conjugate base, then I'm looking for the one with the lower pKa. The lower pKa, chloroethanoic acid, is the one that would act as an acid. So its salt would be the conjugate base. So I'm starting with acid, that is chloroethanoic, and its conjugate base would be when I remove that acidic proton at the end of the COOH. Remember, that is the proton that is donated when this acts as an acid. A titration was carried out by adding 0.1 mole per decimeter cubed hydrochloric acid to 0.1 mole decimeter cubed aqueous ammonia. So we are adding hydrochloric acid, which is a strong acid, to ammonia, which is a weak base, and we have the titration curve. Which region of the graph represents the most effective buffer solution? Remember, what is a buffer solution? It's a solution in which adding slight amounts, small amounts of HCl would not have significant effect on the pH, or it would not change the pH a lot. So where is it that the pH is not changing a lot? That is in region U. So remember that in that region, that is where it can act as a buffer solution. Which of these is the best indicator to use in this titration? Well, how do we know? We look at the graph and we look at the equivalence point from the graph. So that is the middle of that vertical line going up. That is around 4 point something pH, 4 point something. So we look at the data booklet and we choose the one that is closest to that. So that is methyl red, and that means, as you can see, the pH range is between 4.2 and 6.3. So this is the correct range. So this is the best indicator. The others will either change color at a much lower pH, and that means we've passed the endpoint, or at a much higher pH, and that means it will change color before the endpoint. What is the approximate pH of an ammonium chloride solution? Well, where is the ammonium chloride solution? Remember, the ammonium chloride solution is when it has been neutralized and we're starting to go down in that graph. So that vertical line going down at the beginning is about 5.8 pH. A diprotic acid was titrated with sodium hydroxide solution. A 25 centimeter cube portion of 0.1 mole per decimeter cube sodium hydroxide solution required this amount of the solution of the acid for complete neutralization. What is the concentration of the acid? Well, let's calculate. We have volume and concentration of sodium hydroxide, so I can get the number of moles of sodium hydroxide that we used. Then from the equation you can see that the number of moles of acid would be half of that, because the equation says 1 mole of the acid reacts with 2 moles of sodium hydroxide. So the number of moles of acid is half of that, and I can get concentration of the acid, that is number of moles over the volume used. So this would be the concentration of the acid. A sample of bromoalkane containing a single optical isomer. So we're talking about something that is optically active, reacts with hydroxide ions in an SN1 mechanism. Now, what is SN1 mechanism? You should remember that this is the SN1 in which we have the halogenoalkane changing to alcohol. Now, how does it change? The bromine leaves first, because that's the slightly negative end. So the electrons go to the bromine and that leaves to form a carbocation, and then the hydroxide ions attack the carbocation. So we're saying that this is the SN1 mechanism. From this information, it can be deduced that RBR is most likely to be what? Remember that the SN1 mechanism happens if I'm starting with a tertiary halogenoalkane. So a tertiary would react in this way, and it says the alcohol formed is a racemic mixture, and that's another indication that we're going through the carbocation. A compound X with molecular formula C5H10O gave an orange precipitate with 2,4-dinitrophenylhydrazine, and it gave a silver mirror with Tollens reagent. Which of these could not be X? Well, let's see. X gave orange precipitate with 2,4-dinitrophenylhydrazine. Which kind of compounds do that? Remember, this is a test for aldehydes or ketones. So from that first reaction, X could be an aldehyde or a ketone. But when it reacts with Tollens and gives a silver mirror, this is a test for aldehyde. So that means that X is an aldehyde, not a ketone. So which of these could not be X? It is the one that is a ketone. If you can see, all the others are aldehydes except the one in D. So that's a ketone that cannot give silver mirror with Tollens reagent. Propyl ethanoate is hydrolyzed with aqueous sodium hydroxide. Which products are formed? Well, let's take a look. Propyl ethanoate is this. Now, when we hydrolyze it with aqueous sodium hydroxide, remember we are breaking the ester linkage. This gives a part that's an alcohol and a part that is the sodium salt, because we're using sodium hydroxide. So the part that was the acidic part, the C double bond OO something, that is the sodium salt. So which of these is the correct formula? You can see that this one is the correct formula, the sodium ethanoate and propanol or propane 1-ol. 2.95 grams of ethanoic acid is produced from 2.5 grams of ethanol. What is the percent yield? Remember, how do we calculate percent yield? We take a look at the equation. We get the number of moles of what we're starting with. So we're starting with 2.5 grams of ethanol. What is the number of moles? Mass over molecular mass of ethanol. So this is the number of moles. Now, theoretically, by calculation, how much ethanoic acid should we get? Well, the equation shows that they are 1 to 1, so the number of moles of the ethanoic acid should be the same as the number of moles of ethanol, and that means I can calculate the mass of ethanoic acid that we should get. So this is the theoretical yield. Number of moles times the MR of ethanoic says we should get 3.26 grams. Now, how much did they actually get? They got 2.95 grams of ethanoic acid, and that means the percent yield is the actual 2.95 over the theoretical that we calculated, so that is 3.6 times 100, that gives a yield of 90.5%. A mixture of organic compounds was analyzed using thin layer chromatography. Again, I'm going to remind you that thin layer chromatography means I have a glass slide covered with a layer of silica, and we put a spot of the sample, put it into a mobile phase, which is a solvent, and the solvent carries the spots up. Now, we're saying the RF value was 0.92. If the RF value is 0.92, that means the spot went up a lot. So, a very high spot. What can be deduced about the attractions between that component, the substance we're analyzing, and the stationary and mobile phases? Now, if my spot goes up very high in the chromatography, that means that is it more strongly attracted to the stationary or more strongly attracted to the mobile? You should know that when it goes up a lot, that means the attraction to the stationary or to the layer of silica is very weak, while the attraction to the mobile phase or the solvent that is going up is strong, so it goes up with the solvent and we have a high RF value. Okay, section B, the first question says, this question is about carboxylic acids and their derivatives. Lactic acid is produced in muscles as a result of anaerobic respiration, and this is the structure of lactic acid. Now, give a reason why lactic acid shows optical isomerism. What do we mean by optical isomerism? Remember that an optical isomer is one that has a chiral center. What do we mean by a chiral center? A carbon that is attached to 4 different groups. So this would show optical isomerism because it has a chiral center, carbon bonded to 4 different groups, and that means if I draw its mirror image, the mirror image would not be superimposable on this one. So this means we have optical isomers. A laboratory sample of lactic acid does not rotate the plane of plane polarized monochromatic light. Give a reason. So we're saying that lactic acid has a chiral center, and that means it should rotate the plane of polarized light. But if the question is saying that our sample of lactic acid does not rotate it, that means we actually have a racemic mixture. Now, what's a racemic mixture? It's containing equal amounts of both enantiomers, and each of them would want to rotate the plane of polarized light in opposite directions, so there is no net rotation of plane polarized light. Remember, when we have a racemic mixture, that means we have equal amounts of both enantiomers, so there will be no net rotation of the plane of polarized light. Give the structure of the organic product formed when lactic acid reacts with concentrated phosphoric acid. Okay, let's remind ourselves, what does concentrated phosphoric acid do? What we have here is an alcohol. If we add concentrated phosphoric acid, it removes an H and an OH, and it forms an alkene. So that means if we use concentrated phosphoric acid on this, we are actually forming the corresponding alkene. A reaction scheme involving butanoic acid is shown. So we're starting with an alcohol. We added acidified potassium dichromate and heat under reflux, and we ended up with an acid. So what is the alcohol? If I'm ending up with butanoic acid, that means I am starting with butane 1-ol, because this is the one that would be oxidized to form an acid. Then we're adding reagent Y to the acid, and we're changing it to acid chloride. Which reagent will change acid to acid chloride? Well, you should add phosphorus pentachloride, or PCl5. Now, the acid chloride is reacting with methylamine. Now, when we react it with an amine, what happens? The nitrogen attacks the double bond and replaces the Cl. So this amide, which would be N-methyl butanamide, that is the product for that reaction. The repeat unit of a polyester is shown. Give the structures of the two monomers that could form this polyester. Okay, this is a polyester. It has an ester linkage in the middle. What were the monomers that we joined to form this polymer? Remember, in order to get the monomer, I break it at the ester linkage. There is a monomer on the right and a monomer on the left. Now, the one on the right is the one that has a double bond O, so that would be the acid. Now, the one on the left is the one that has oxygen. That means that was the dialcohol, where we removed the H in order to join it. And the other one is the diacid, where we remove the OH to join them together. An organic compound E contains carbon, hydrogen, and oxygen only. The accurate relative atomic masses of the three elements are shown. E contains 5 carbon atoms. It has a total MR of 102.0678. In the mass spectrum, deduce the molecular formula of E. So we know it has carbon, hydrogen, and oxygen. And we know it has 5 carbons. So if we say 5 times 12 and subtract it from the total, then I'm left with about 42. So 42 means how many oxygens could I possibly have? Well, if I say only 1, then I would have too many hydrogens. If I say anything more than 2, then I don't have enough hydrogen. So most probably the oxygen is 2 of them. so that I'm left with 10. Now the 10 divided by the atomic mass of each hydrogen, that means I have 10 hydrogens, and that means that my formula is C5H10O2. Aqueous sodium hydrogen carbonate is added to a sample of that molecule. No effervescence occurs. Remember, we found 2 oxygens. 2 oxygens could mean that it is an acid, or it has acid and something else, or it has an alcohol or 2 alcohols, something like that. But if we test it with sodium hydrogen carbonate and no effervescence, that just tells us that it is not a carboxylic acid. And then if it says the infrared spectrum has an absorption in the range 1750 to 1735, well, I look at the data booklet and I find that the one that gives an absorption in this range is the ester. So this is the absorption for the C double bond O of an ester, and that means my compound is an ester. Data from the high resolution proton NMR is shown. Deduce the structure of E and justify your answer by labeling the protons responsible for each peak. Okay, we know the formula. We know it has C5H10O2. And we said it's an ester. So if we say that it is this is something that has 5 carbons and it's an ester. Now, does this agree with the high resolution proton NMR? Well, yes. Let's take a look. A is a triplet with 2 hydrogens. So that's the CH2 next to the O of the ester. B is a singlet with 3 hydrogens, so that's the methyl group on the right. C is a sextet, that means it is the CH2 in the middle there, in which it is surrounded by 2 hydrogens from one side, 3 hydrogens from the other, so that's 5, so it would form a sextet, and it is due to 2 protons. And the D is that methyl group on the left end. That's a triplet because it has 2 protons next to it, and it is due to 3 protons. Remember, the splitting pattern tells you how many protons on the neighboring carbons, and the relative peak area tells you how many protons give this specific peak. This question is about sulfuric acid and its salts. The manufacture of sulfuric acid involves this equilibrium. So I have an equilibrium between SO2O2 and SO3, and we're given the delta H is a negative value. Now the question is, a catalyst, vanadium oxide, is used in this reaction. State the effect, if any, of the catalyst on the value of Kp. Now, we should know that nothing affects Kp except temperature. The only thing that would affect Kp or any equilibrium constant is temperature. It is not affected by catalysts. It's not affected by changes in concentrations. It is affected by this. So a catalyst, if I use a catalyst, would that affect the Kp? Well, it would not affect the Kp. Remember that the catalyst speeds up both forward and backward reactions, so it has no effect on the yield. The temperature used for this reaction in industry is 700 K. Explain in terms of the equilibrium constant and equilibrium position the effect of an increase in temperature on the equilibrium yield of sulfur trioxide. Okay, this was the equation, and the equation says that the forward reaction is exothermic. So what happens if we increase temperature? Remember, increasing the temperature would cause the reaction to go backward, Now, the reaction going back means I have less of the SO3, and that means the Kp would also be less. So increasing the temperature causes the equilibrium to shift to the left. Remember, if the forward is exo, that means the backward is endo. Increasing the temperature goes endo. And if it goes back, then the equilibrium constants will decrease because I will have less SO3 produced. Write the expression for the equilibrium constant. Well, this was the expression for the equilibrium constant, Kp. Remember that Kp is the partial pressure of the products, so the power of their coefficients divided by the partial pressure of the reactants to the power of their coefficients. A mixture of 2 mole of sulfur dioxide, 1 mole of oxygen is allowed to reach equilibrium at 5 atm pressure. So the total pressure is 5, and we're starting with 2 moles of sulfur dioxide, 1 mole of oxygen. Now 1.6 mole of sulfur trioxide is formed at equilibrium. Calculate the value of Kp. Usually when we have a question like this, we do what we call the ice chart. So initially, what did we have? Initially, starting at the beginning, we had 2 mole of sulfur dioxide, 1 mole of oxygen, and nothing of the SO3. Then what would happen? What would be the change? Remember that the change has to do with the coefficients. So 2SO2, that means I'm going to dissociate or react 2x of what we started with, and I'm going to react x of the oxygen to give 2x of the SO3. The question says that what I have of SO3 at the end is 1.6, and that means the 2x is 1.6, and that means x is 0.8. Now we go back and determine what we will have at equilibrium. At equilibrium, I will have what we started with minus the 2 times 0.8 or 1 times 0.8 and so on. So these are the equilibrium number of moles. The total number of moles is 2.2. Now, how do we determine Kp? We need the partial pressure of each of these. How do we get partial pressure? Mole fraction times total pressure. Mole fraction means the number of moles of what we're talking about divided by the total number of moles times the total pressure. So for SO2, it's 0.4 divided by the total times 5 because that was the total pressure, and so on for the others. So this gives values for the partial pressure of each of these gases. Put them into the equation for Kp and determine the units also. So this comes out to Kp of 35.2 atm to the minus 1. Sulfur trioxide is used to produce sulfuric acid. Commercial concentrated sulfuric acid contains 98.5% sulfuric acid. The density of that solution is 1800 grams. Calculate the concentration. So the density in 1 decimeter cubed is 1800 grams. But we're saying that our solution has 98.5% of that. So our sulfuric acid solution has 98.5% of the 1800. So that gives this mass in 1 decimeter cubed. Now we can go on and determine. We know that the MR, I can calculate it. It comes out to be 98.1. So I can get the concentration in 1 decimeter cube. That would be changing the mass to moles. So this gives 18.07 mole in 1 decimeter cube. The pH of a 0.1 mole per decimeter cube solution of sulfuric acid is 0.97. Calculate the concentration of hydrogen ions. How do we get concentration of hydrogen ions from the pH. Remember, concentration is 10 to the minus pH. So 10 to the minus of 0.97 is 0.107. In an aqueous solution of sulfuric acid, the following equilibria exist. Remember that sulfuric acid is something that is diprotic. That means it has two H plus ions. So the first H plus ions dissociates to give HSO4 minus. And the equation says that the Ka is very large, and that means that this equation is far to the right. So most of the H2SO4 will dissociate to give HSO4 minus. But then the HSO4 minus, in order to dissociate and change into sulfate ions, the Ka is small. Explain in terms of these equilibria why the concentration of hydrogen ions in 0.1 mole decimeter cubed of sulfuric acid is not 0.2. Now, for a diprotic acid, that gives 2 protons, 2H plus, so the concentration of H plus ions should be actually twice the concentration of the acid. So why isn't it twice? Well, that's because we said the Ka for that first equation is very large, so the equilibrium is far to the right, and I get a lot of H plus from the first dissociation. But then for the HSO4 minus to dissociate again and give more H plus, this is a very small Ka, so it is very little amount that is produced, and it will not contribute a lot to the actual total concentration of H plus ions. A buffer solution is made from HSO4 minus and sulfate ions. Write 2 ionic equations involving HSO4 minus and sulfate ions to show how this solution acts as a buffer. Remember, this is what we have. I have HSO4 minus, it breaks up to form H plus and sulfate ions. Now, if we add a little bit of acid or a little bit of base, it shouldn't affect the overall pH a lot. That's how we determine that's going to be a buffer. Now, why is it that adding a little bit of acid or a little bit of base would not affect the overall concentration of H plus ions? This is because if we add a little bit of base, it will react with the acid, which is the one on the left, to form sulfate and water. If we add a little bit of acid, then it reacts with the conjugate base, which is sulfate ions, to form the HSO4 minus, so it keeps moving the equilibrium forward and backward, so that there is very little change in the overall concentration of H plus ions. A buffer solution is formed by mixing 25 centimeter cubed of a solution, that is 0.15 mole per decimeter cubed, with respect to sulfate ions, and this amount of solution and concentration with respect to HSO4 minus. Calculate the overall pH of this buffer solution, and we're given the Ka of HSO4 minus. Okay, for these kinds of questions, well, we need to get the concentration of sulfate ions in the mixture and the concentration of HSO4 minus in the overall mixture, and then we can use that to get pH. So, the number of moles of sulfate ions is concentration times volume. But what is the concentration of the sulfate ions in the solution as a whole? Concentration would be the number of moles over the total volume. Remember, we have 25 centimeter cubed of the sulfate added to 75 centimeter cubed of the HSO4 minus. That's a total of 100 centimeter cubed, or 0.1 decimeter cubed. So the number of moles for sulfate over the total volume gives this concentration of sulfate ions. We do the same for the HSO4 minus. Now, the number of moles is concentration times volume. Now, the concentration overall of the HSO4 minus is that number of moles over the total volume, which we said is 0.1. Now that we have the concentrations for each of them, I can put it into this equation. pH is equal to pKa plus log of the concentration of the sulfate ions over the concentration of the HSO4 minus. So put in the values. We have the Ka, so the pKa is minus log of that, plus log of the concentrations we just got. This gives an overall pH of 1.62. Question 19 is about carbonyl compounds. We are given the skeletal formula of menthone. Give the molecular formula of this compound. Of course, in order to get the molecular formula, I write it out to see where is the carbons, hydrogens. Remember, each carbon must have a total of 4 bonds. If it doesn't have 4 bonds, then you complete it with hydrogen. So this is the molecule, and if we add all the number of carbons, hydrogens, and oxygens, it comes out to C10H18O. Ethanol reacts with hydrogen cyanide in presence of cyanide ions to form 2-hydroxypropane nitrile. So this is the reaction of cyanide with an aldehyde. Draw the mechanism for this reaction. Include curly arrows, relevant lone pairs, and dipoles. We're starting with ethanol. We're going to have the cyanide ion. Remember that the cyanide ion has a lone pair of electrons, and the carbonyl of the ethanol, the carbon is slightly positive, the oxygen is slightly negative, of course, because oxygen is more electronegative than carbon. So the electrons, the lone pair of electrons from the cyanide attacks the slightly positive carbon, and the electrons of the double bond go to the slightly negative oxygen. Then we're saying this is reacting with hydrogen cyanide in presence of cyanide ions, so the lone pair of electrons on the O minus now reacts with the H of the cyanide, and this gives the overall product, which is a cyanohydrin. A carbonyl compound F has the formula C6H12O. Now, the first thing we know about F is that it reacts with iodine in alkaline solution to give a pale yellow precipitate. What kind of compound reacts with iodine in alkaline solution? Remember, this is what we call the iodoform test. And this is a positive test. We get the pale yellow precipitate when we start with something that has this group, which is the methyl ketone, CH3C double bond O. Or you could just write it CH3CO group. Draw the skeletal formula of 4 possible structures of F. So we know that this is the formula, C6H12O, and we know it should have a CH3C double bond O. So what are the possible structures? These would be the possible structures that we have. All of them have a methyl ketone, and the rest of the carbons would be arranged in different ways. So these are the 4 possible structures. The carbon-13 NMR of F has 4 peaks, so identify F. We said these are the 4 possible structures, and the question now is, which of these would give 4 peaks in the carbon-13 NMR? 4 peaks means 4 carbons or 4 carbon environments. So if we're looking at that first one, all the methyl groups at the left end are one type of carbon, and then the carbon that's attached to them, that's another, and then the carbon of the carbonyl is a third, and the carbon of the methyl on the right is a fourth. So actually this is the one that has 4 peaks. The others will give more than 4 peaks if you're looking at it. So this is the formula that we're looking for. Now, the question says, draw its displayed formula and justify your answer by labeling the carbon atoms or groups of carbons responsible for the 4 peaks. So we said the 3 methyl groups on the left end are all similar. The carbon attached to them, that's another one. The carbon of the carbonyl is a third, and the carbon of the methyl group on the right, that is the 4th type of carbon. Explain in terms of all the intermolecular forces involved why butanal has a higher boiling temperature than pentane, but a lower boiling temperature than propanoic acid. So you need to explain all the intermolecular forces for each of them. So let's take a look at pentane. You should realize that pentane is an alkane, so it has only London forces between molecules due to the distortion of the electron clouds. Now, these London forces are very weak intermolecular forces and need a small amount of energy to be broken, and that's why it's less than butanal. Now, butanal is something that's an aldehyde, so in addition, please remember to include somewhere that in addition to the weak London forces, it also has permanent dipole-dipole interactions due to the presence of the electronegative oxygen. So this forms dipoles, permanent dipoles in the carbonyl, and these kinds of interaction need more energy to be broken, and that's why its boiling temperature is higher than that of pentane. Now, what about propanoic acid? Propanoic acid is an acid. It can form hydrogen bonds between its molecules. These are stronger intermolecular forces than the others. So it also has permanent dipole-dipole, and it has London dispersion forces. Remember, all of these simple molecules have London dispersion forces. If they have an electronegative element, then they probably have permanent dipole-dipole. But if they can form hydrogen bonds, these are the strongest intermolecular forces between these molecules. There's need more energy to be broken, and that is why its boiling temperature is higher than butanal. Please be careful when you're explaining this kind of questions. Okay, section C. This question is about some compounds of bromine. We're starting with potassium bromate. It decomposes to form potassium bromide and oxygen, and we're given the standard molar enthalpies of these substances, and we're given the delta H of the reaction. Calculate the total entropy change. You should know that the total is the system plus the surroundings. So let's do the system first. The delta S of the system is the total of the entropies of products minus reactants, and please take into account the coefficients. So we have 3 of oxygen plus 2 of KBr minus 2 of the potassium bromate. This gives an overall delta S system of plus 508. Do not forget to write the signs. The plus or the minus should be written out. Now, what is delta S surroundings? How do we get delta S surroundings? It's minus delta H over T. So we have the delta H given up there, and we're saying we're at 298 K. So this is the delta S surroundings. Remember that the equation is minus delta H over T. If the delta H is already minus, then the overall delta S surroundings is a positive value. You have to show that. And of course, the delta S total is the system plus the surroundings, and this comes out also to be a positive value. Bromide ions react with bromate ions in acidic solution. 2 experiments were carried out. So in experiment 1, the concentration of bromide ions is determined at different times. Concentration of bromate and H plus ions are in large excess, and we get this graph of concentration of bromide ions against time. determine the order of the reaction with respect to the bromide ions. Of course, if we're given the graph and we want to know the order, then we take a look at the half-life. Half-life means the time taken for the concentration to become half. So that first, from 0.1 to half of that, that's 0.05, it took 200 seconds. And then from 0.05 to half of that, 0.025, it also took 200 seconds. So if the half-life is constant, that means the reaction is first order. Remember, to be first order, the half-lives have to be constant. Now in experiment 2, the initial concentrations of bromate and H+ ions are changed and the initial rate of reaction is determined. So the initial concentration of bromide ions is constant and in large excess, so we're not going to take that into consideration, and we look at the information in the table, determine the order of reaction with respect to bromate and H+. So what do? If we choose run 1 and 2, the H+ is constant. Now we look at the bromate. We're doubling the bromate. What happened to the rate? The rate doubled. When we double the bromate and the rate is doubled, that means the reaction is first order with respect to the bromate. So remember, we're trying to choose 2 runs in which one of the concentrations is not changing while the other one is doubling or tripling, and we see the effect on the rate. So from these information, it is first order with respect to bromate, because as I doubled the concentration of bromate, the rate doubled. Okay, what about to get the effect on concentration of H+ ions, where we don't have something where the bromate is constant? So we look at, for example, run 1 and 3. Now, in run 1 and 3, the bromate is tripled. The H+ is doubled. What happened to the rate? The rate increases by 12 times. That means that it is second order with respect to H+. Give the overall rate equation. So we found that it's first order with respect to bromide, first order with respect to bromate, and second order with respect to H+. So this is the rate equation. Rate is equal to K times all of these. Now, the question is asking for units for the rate constant. So we rearrange the equation to get K and determine the units for each of these and cancel whatever is the same up and down, and we're left with decimeter to the power 6, mole to the power -3, and seconds to the power -1. The rate constant for the reaction between bromoalkane and cyanide ions is determined at 5 different temperatures. So we have a table and we are required to plot a graph. So when we plot the graph, you should realize that from the table, you try to use as much of the graph as possible. Plot the points. So this is a graph of 1/T versus length K. Then join the points with the best fit straight line. Then the question says we want to get activation energy. And to get activation energy, this is the graph that we drew. The question was plot a graph of length K versus 1/T and use it to determine activation energy. Include sign and units of the gradient and activation energy. And we use the Arrhenius equation. So remember, if we have this kind of graph, the gradient we get. So from this graph, we got the gradient to be about minus 12,813. Of course, these actual numbers could differ from one student to another due to the changes in the line, but it should be within this range. So that's the gradient, and this is a negative gradient. And then you should know that when we want to get the activation energy from this kind of graph, the activation energy would be minus the gradient times R. So if the gradient comes out negative, then the EA comes out as a positive value multiplied by 8.31. We end up with this kind of number. Divide by 1,000 to change it to kilojoules. So this comes out about 106.5 kilojoule. And that's the end of this paper. I hope this was useful to you. Thank you for listening.